I'm Hiroaki Miura from University of Tokyo. And at first, I'd like to thank Professor Shu and Ken Hilder for giving me a chance to have a talk here. And he introduced me as an expert, but I'm not so good at modeling and other things. Anyway, today the title of my talk today is Recent Studies Using a Global CRM. And at first, I'd like to give an overview of the non-hydrostatic ixhedral atmosphere model. And at first, I'd like to give an overview of the non-hydrostatic ixhedral atmosphere model NICAM. And after that, I want to introduce some of the recent and future updates of NICAM model, some of the things that I'm working on now. I mentioned from the simulation using horizontal mesh size less than 1 kilometer, and the other is an MGO stuff. Anyway, first back to the cloud parameterization issue. And as you know very well, the cloud parameterization framework is very variable to test our knowledge or understanding about the nature of clouds. And we still do not understand how strongly the clouds are controlled by large scales. And also how strong the cloud feedback to large scale is, of course, an unknown issue. And the cloud parameterization assumes an artificial scale separation for the spatial scales that there is no separation in nature as it was confirmed from observations. For the spatial scales that there is no separation in nature as it was confirmed from observations. So that is, there are a lot of remaining issues around the cloud parameterizations. Anyway, that is an interesting problem, but in terms of numerical modeling, that is a very, very strong cause of uncertainties in climate simulations. And Dave Randall called it as cloud parameterization deadlock in 2000 paper. And he published a paper titled Beyond the Deadlock last year, and he gave an overview for these past 10 years activity to overcome this deadlock. And one important activities in the last 10 years may be the super parameterization or the multi-scale modeling framework. The first trial was done by Dr. Grabowski in 2001, and at the same year, Marat and Dave Randall published a very similar approach in a letter. Anyway, the super parameterization uses a cloud resolving model, 2D or the very small size 3D model inside climate model in place of conventional parameterizations. And the other approach to overcome the deadlock may be our high resolution modeling activity. Dr. Mazno is very famous for his equatorially trapped wave theories. And he is also very famous for his theory for the stratospheric sudden warming. And he is still alive. And he's now not working on the methodology for his theory for the stratospheric sudden warming. And he is still alive. And he's now not working on the meteorological field. He's now working to develop he is still alive. And he's now not working on the meteorological field. He's now working to develop equation sets for plate tectonics. And he wants to predict earthquakes in future. He do not think that he can do it within his lifetime, but he is very enjoying about that now. Anyway, he wants to have a model that can simulate spontaneous behavior of clouds about 10 years ago. And that model requires horizontal resolution less than 10 kilometers to avoid cumulus parameterization issues. And Professor Sato decided to realize his dream 10 years ago with Dr. Tomita, who is now leading our group in NICAM Kobe, where the K-computer is. And in my point of view, Professor Sato is a strong leader, and I respect him, but NICAM dynamic core was coded by him more than 90% or so, I think. And I want to mention, before going to my study, the cross-zoning model cannot solve all of the issues related to clouds. Here I show many uncertainties in climate models, in conventional climate models, and cloud-related quantities are not simulated explicitly. Area, as somebody mentioned in the morning talk, area is not simulated explicitly in the model, and this height and figure flux are all implant issues in cumulus parameterizations, and the other processes are important. With using cloud resolving approach, we can compute these quantities at least explicitly. I don't want to say that these quantities are exactly or quite simulated with this model. We can simulate or directly compute these quantities in the cloud resolving model. And so that fact may benefit us because, for example, the cloud area, by computing cloud area explicitly, we can estimate the cloud radiation interaction explicitly. I do not want to say it's correct or not. And we can compute direct interaction between cloud and cloud issue. But with cloud system resolving models, entanglement and turbulent issues remains, and the microphysics issues are another deadlock for our cloud resolving our global climate simulations. And turbulent mixing in the low clouds is also still an important problem. And all these processes controls the dry or moist in the free troposphere, and this is very important to have good climate simulation. So back to 2002, when Dr. Sato started the development of NICAM, the Earth simulator was developed in Japan, and it was ranked in the first place of the top 500 list. And 12 years have passed since this time. 12 years is an important unit in the Eastern Asia anyway. And this is 12 years ago. And at that time, not only the NICAM, but also the microclimate model is benefited from this computer. The horizontal resolution was increased from 240 to about 100. And that was the highest resolution model is IPCC AR4. And when we started, this is just a historical overview about our knowledge about that time, about the dynamical core development. In this age, we thought, or we believed that the spectral method would die in near future because of the high computational burden of the Legendre transformation in high-resolution simulation on massive parallel machines. But we now know that the ECMW spectral model is fast even for the T8000 on parallel machines. And the other thing is that there was only one icosahedral grid model at that time. That is the grid that predict vorticity and divergence. And it requires Poisson solver to have velocity potential and stream function to reconstruct velocity field. And Poisson solver, we believed that Poisson solver also do not work on massive parallel machines. But now we know that multi-grid method is efficient even for more than 80,000 cores. And our C-grid approach on hexagonal mesh was questioned because of the non-stationary lossy wave. That is a computational mode due to the mismatch between the degrees of freedom of pressure and the velocity points. But now there was a cure, not a perfect cure, but some marginal cure for that non-stationary lossy wave. Dr. Subban and Dr. Gassman published a paper about that. And at that time, we are not familiar with this continuous Galerkin local spectral element-like method. But now NICAM is developing a spectral element core, and this continuous Galerkin is also a choice now. And at that time, several kilometer grid cell was called cloud resolving in some papers, but now it is prohibited to call that as cloud resolving, and we are using cloud system resolving. I don't know what the cloud system resolving means. Cloud size depends on horizontal resolution. Anyway, this time we are calling this as cloud resolving. So from the current knowledge about the dynamical core, the choice using Arakawa A grid and icosahedral grid might not be the best one at the time. But if we remember the fact that the NICAM model was the only one working global CRM for nearly 10 years and after 2004 may shows that this choice by Dr. Sato and Dr. Tomita might not a bad choice, I think. Anyway, the NICAM adopted icosahedral grid because this is a closer uniform grid over, this can have closer uniform mesh over the globe. And Arakawa A grid arrangement was chosen to avoid Poisson solver. And finite volume method was chosen to conserve mass and total energy for longer time simulations than usual cloud resolving model approach. And to achieve very efficient computation on the Earth simulator and to save memory space, a second-order centered spatial discretization was chosen to minimize stencils. And that is a positive point. The negative point is that at that time, we do not have a higher order operator option. We have not developed third order or fourth order schemes on the icosahedral grid. And in developing the model, we learned much from JMS, CSC, and NCAR. For example, the icosahedral grid was suggested by Professor Dave Randall. And following vertical coordinate, we learned much from JMA experience. And sand wave treatment, we followed Bill Skamarok's paper, and so on. So next slide shows an example of icosahedral grid. And many guys are very familiar now, I think, but somebody may not. The icosahedral grid is made from the icosahedron, and we split each edge of the triangle, bisect this, for example, bisect this edge, and make a new point as a center. And this point is projected onto the sphere, and this becomes a new point. And we have a level 1 grid. And recursively applying the method, we can have final mesh, triangular mesh. And based on this triangular mesh, we made a hexagonal or pentagonal control volume on the sphere. And this is an example of the grid mesh having 480 kilometer resolution. And this is 240 Japanese here. And no Taiwan, I'm sorry. But 120, this interpolation recognizes Taiwan here, and so on. And higher resolution. And 3.55 or 3.5 resolution was used on the simulator. This is the highest. And after making a triangular mesh, we need to apply a grid optimization algorithm to have better shaped hexagonal mesh. And this is required to have accurate computation of divergence, gradient, rotation operators using a finite volume approach. Without this grid optimization, those figures show the horizontal axis is some grid resolution stencil, and the vertical axis is a measure of error. And with higher horizontal resolution, the error decreases. And this is and by using this spring method, we have better accuracy of this grid. And these are very important in high resolution simulations because these errors, discontinuous errors for each cell can generate noise-like structure around highly deformed hexagons. So this is a summary of the dynamics paper for in-house development of NICAM. Tomita published horizontal discretization. Tomita shows horizontal in-house development of NICAM. Tomita published horizontal discretization. Tomita shows horizontal discretizations and also shows 2D shallow water test results. And he explains details about the spring dynamics optimization of the grid. And Dr. Sato developed, he brought some and noise from equations used in NICAM. And Tomita and Sato shows first results of dynamical core in 2004. And I added only a small contribution in my model now. And we used a microphysics scheme by Grabowski's in the early stage of the model. In 2008, Adobe developed this new microphysics scheme based on this scheme. Not good to enforce this scheme also in program and I watching microphysics for 1.5 years. But anyway, that is another story. And after testing our mode, and our physics are always tested with some flex grids and with some And after that, we advanced the Aka balance simulation, and this is the result from his first global cloud resolving simulation using 3.5 kilometer mesh. And you may see an eastward moving system around here, and that this system has very similar. The most important thing we learned from this simulation is that a conventional CR framework can simulate spontaneous organization of clouds if it is just used over the globe, if it is just applied to the globe. Nothing new. There are many things are new, but other idealized or the framework are realistic organization of clouds. And we want to know if this type of organized system has some counterpart in the global simulation and goes to a realistic simulation that I performed in 2007. And this is a simulation of a Martin-Julian oscillation event occurred in December 2006. And this is a demonstration. At this point, we began to solve that systems initially and have some reality. But at this time, it was very difficult to confirm if the NICAM simulation has robustness. We are wondering if this performance to transfer data to estimator to our local machine, and data conversion needs 1 more month. And making this one figure requires 5 minutes, 2 minutes. It was very hard to figure, and it was very hard to check offsets automatically. This figure is from the Skamrock and Gassman 2011. As you may know, Skamrock is developing his hexagonal grid model for M-Pass in M-Pass, and Dr. Gassman is developing another hexagonal non-hydrostatic model in Germany. The scheme is like this, and these black circles shows some different solution of cosine-shaped transport test. And Williamson's test case includes test case, transport test case, and this was different solutions of properties. And this shows that several tenders has a huge pressure particular. And data shows in the player can be good. But if we are very high, this is a conventional third-order scheme form. And we can change the form into this. And it includes center interpolation and some, if you are familiar with numerical modeling, you see that this is estimate they use this form to reconstruct third-order scheme on the hexagonal mesh. But unfortunately, it has a length scale here. With a Bologna mesh, Skamrock's model and Gassman's model is based on the Bologna cell. That ensures also, but it uses non-Bologna cell constructed in this way. And in the Bologna cell case, we determine the hexagonal vertices as the ortho center of this triangle. These are ortho centers. A more regular hexagon can be generated, and this is good to have more accurate discretization of operators. But there is a strong weak point as also narrative loss. And in this case, this distance between two computational nodes is not a reconstruction of second-order profile on the hexagonal mesh. And this is an example of the 1D case. And there are 3 missing ratios, and I want to reconstruct second-order profile inside this. And the second-order profile has 3 unknown constraints that says that integral within this cell of this profile is equal to the Q cross delta X inside. The mass included in a cell must be satisfied because there's a reference solution, and this is a second-order centered case used in NICAM, and this is a new scheme I'm using. And for the other passive, I and Bill Skamrock developed another travel scheme for passive tracers. And this is a NICAM's one based on piecewise linear. With a second-order profile, we can get better results. And with another more local second-order profile, we can capture discontinuity more sharply. This is just a demonstration. And secret, as I mentioned before, this locates pressure of some other scalar and divergence and velocity at the center of hexagon. And in every case, we place such scalars on center, and velocity is also located at the center. The number of centers in this case, so the computational mode is allowed in for the velocity point. And now I'm working to manage that kind of thing. Anyway, for a geometry adjustment test on the using the shallow water model, in every case, for responding to this one grid forcing, it shows a very wavy pattern due to the previous noise. It is working well on the icosahedral grid. Time is very wavy pattern due to the previous noise. It is working well on the icosahedral grid. Time is anyway. And another important update that it is working well on the icosahedral grid. Time is anyway. And another important update that this is not relating to the physics and dynamics, but time is anyway. And another important update that this is not relating to the physics and dynamics, but this is a very strong tool to tune microphysics. Important update that this is not relating to the physics and dynamics, but this is a very strong tool to tune microphysics. And Dr. Hashino, he's now working in academic dynamics, but this is a very strong tool to tune microphysics. And Dr. Hashino, he's now working in Academia Sinica here and sitting there, has developed geophysics. And Dr. Hashino, he's now working in Academia Sinica here and sitting there, has developed a joint simulator. And we are using this now working in academia Sinica here and sitting there, has developed a joint simulator. And we are using this J simulator to reconstruct a satellite signal. Has developed a joint simulator. And we are using this J simulator to reconstruct a satellite signal from the model fields. And that enables this J simulator to reconstruct a satellite signal from the model fields. And that enables direct comparison of the model signal and observed signal. A satellite signal from the model fields. And that enables direct comparison of the model signal and observed signal. And this shows that the NICAM's organization is very. That enables direct comparison of the model signal and observed signal. And this shows that the NICAM's organization is very weak or confined to the center of the class. The class seems to and observed signal. And this shows that the NICAM's organization is very weak or confined to the center of the class. The class seems to be very strong in the NICAM. Anyway, such kind of direct organization is very weak or confined to the center of the class. The class seems to be very strong in the NICAM. Anyway, such kind of direct comparison, and we can make statistics using this. The class seems to be very strong in the NICAM. Anyway, such kind of direct comparison, and we can make statistics using this J simulator now. And kind of direct comparison, and we can make statistics using this J simulator now. And what's next? I want to introduce about using this J simulator now. And what's next? I want to introduce about the K computer enabled us to do. And what's next? I want to introduce about the K computer enabled us to do. One thing is this introduce about the K computer enabled us to do. One thing is this 807-meter simulation for just. One thing is this 807-meter simulation for just 2 days. So 2 days is 2 days for 807-meter simulation for just 2 days. So 2 days is 2 days for global simulation. I don't know how scientific is it. Just 2 days. So 2 days is 2 days for global simulation. I don't know how scientific is it. Anyway, this is a very interesting movie made by Dr. Yoshida in Kobe IX. And this result was introduced by Dr. Miyamoto's paper published last year in Geophysical Research Letters. And with NICAM was chosen as a target application in the development of K computer. And NICAM's dynamics and physics are very strongly tuned for this K computer. A large part of the code was changed for computational efficiency. And it enables, in the estimator time, 3.5 kilometer is the finest resolution, but now it allows 870 meter. And for 3.5 kilometer horizontal resolution, it allows 1 month simulation within 2 days, real time. It is very strong. But, and as I have resting iPhone and AJ-like system is simulated better than 3.5 kilometer time. But this is one achievement. But the other important achievement is that it allows us to make ensemble simulation to check robustness of NICAM simulation about MJO. Not only MJO, but other things will be possible, of course. Anyway, these are the example of the MJO simulation, and this work was done by Dr. Miyakawa, very strongly collaborating with me. And his result was published in Nature Communications this year already. Anyway, these are the Hofmerer diagrams of outgoing long wave radiation for 40 day simulations. The time is from up to bottom. And this case, for these cases, some MJO simulation seems to be good, but this is not so good, I think. Anyway, with only one case simulation, we cannot evaluate or we cannot make some statistics. But now we can make some statistics and evaluate NICAM simulation quantitatively. And to make some statistics, we choose MJO events based on these criteria. We used years from 2003 to 2012, and winter is chosen because it includes a strong MJO event. And average amplitude of phases from 2 to 5 is greater than 2 is a criteria in RM diagram. RM method is very familiar in the MJO research. That is a projection onto some specific patterns. For EOF1 and the EOF2 span the phase space. Anyway, based on these criteria, we choose 19 MJO cases, and after that, we made initial conditions for different phases. Stage phase 2 choose as the first enter is chosen. And simulate score of 9 formula. Horizontal 24 to 28 days. These numbers do not depend strongly on the initial date of the simulation. The phase 8 is relatively worse comparing to phase 1 and phase 2, but it keeps 0.6 for nearly 25 days. And not only the correlation, but also the phase speed is not so bad comparing to observation. This shows that time lag composite of phase probability division. So, comparing the data is chosen to the day 1 phase station. No, the phase 3. Phase 2 is a start date, I guess. The first date of phase 3 is chosen the data here. And you see the gradient of this line is basically between observation simulations. That means that this propagation speed is very fast in a simulation. And we can see a very similar thing on the RM phase space. The black line is from observation, and the red line is from NICAM simulation, and NICAM follows the observation line very well. And this shows that this moving speed is good, and not all the gradient phase speed and NICAM reproduce our structures. Of course, these are MJO composite for anomalies. Phase 3 the vegetation anomalies located over the eastern Indian Ocean, and in phase 5, vegetation is located over marine continent, and phase 7 is located in the western Pacific. And in the simulation case, in phase 3, that means that the average days from the initial date about 13 days. This case, 25 days after the initial condition. And this case, 28 days. Even more than 3 weeks. This causes shows us 9 reports. This is special pattern very well for MJO events. And I'd like to summarize my talk. And I showed here new supercomputer enabled severance cloud system developing prediction. And predictability of MJO in about 20 days with 14-kilometer mesh. And we think that we finally get to the start point to study for some science about MJO dynamic or implant processes for the MJO. My work in 2007 and Miyakawa's 2004 may be some demonstrations that the NICAM is a useful tool to simulate MJO, but now we want to use that model for make some science. And other kilometer resolution runs are still demonstrations. 2 days. There maybe we can find some interesting things, but as we interpolate initial conditions from 1 degree data, so the first half day or 1 day is I guess that the energy spectrum in the smaller scale have not been reconstructed inside the model, and we must wait for half or 1 day to make expect model's balance in the model. And so the meaningful time is only 1 day, and 1 day, I don't know if the 1 day average have some meaningful things or not. So we must wait for the next computer to make a better statement in science using this very, very high resolution global simulation. And there are some model upgrades in dynamics physics and satellite simulator. This is a very strong to tune microphysics. Actually, the Dr. Sato's student got PhD this year by tuning Tomita's parameterization to have good statistics about the vertical structure of snow or something, some such kind of species. And this is a very strong tool. And in this talk, I did not talk about that, but Dr. Kodama in the Jamstack have finished EMIP-like simulation for the present day condition and some future day condition, and we want to compare those results, and we are analyzing his data extensively now, and ocean coupling is ongoing now. We want to make some presentations in the future. It's not problem now. Thank you for your listening.
Okay, I have time for one short question.
Do your model has the capability to simulate shear elevation? The cloud is about 1.52 kilometers, and the MGL is, there's a pretty of the convection. Before that, we need a shear elevation to manage the lower troposphere. So, can you comment on that?
Yes, in my understanding, so NICAM can simulate theoretically. So, especially in the 14 integrate. Actually, I have made animation to show convection, as we animation to show convection. And there are, cannot find real problems, as I mentioned.
So the challenge is parameterized?
No, so I think that I'm just wondering if such a pre-control process is very important or not. Such kind of results may question such kind of something.
Okay, let's thank the speaker again and the session.